Alright guys, what I've done is made you a nice little video to sort of alleviate the pressure of going rapid speed next class due to the snow day. What we want to talk about is standard deviation, or sample standard deviation as we calculate it here. So what it is, it's the sum of the difference of all of the values in the set minus the mean, all squared, divided by the number of things in the set minus 1. We'll go over this in a second. What you need to know about standard deviation, most importantly, just get this in your notes, that it describes variability. Maybe add a few more exclamation points. What I have here is just a short little simple set of numbers, 2, 4, 6, and 8. And the first thing we're going to want to calculate in order to calculate standard deviation is x bar, or our sample mean, which is the sum total of 2 plus 4 plus 6 plus 8, all divided by the number of items there are, 4 things, which is 20 divided by 4, which is 5. So x bar is equal to 5. To give myself a little room, I just shrank that calculation down. So for sample standard deviation, what we're going to want to do is follow that method of the sum total of all of the differences between our individual values in the mean squared. By that I mean we're going to take that first number, 2, and we're going to subtract x bar, which was 5. And we're going to take that calculation, we're going to square it, and we're going to add that to a bunch of others. So I'm just going to sort of set them up here, and I'm a little tight for space, so it's 1, 2, 3, plus this last one I'm just going to squeeze in the bottom here. All of these things are going to be squared. They're all going to be minus 5, right? Because we're going to keep subtracting the mean from each of the 3 remaining data values. So 4 minus 5 all squared, and 6 minus 5 all squared, and 8 minus 5 all squared, and that's all going to be divided by n minus 1, where n is the number of items in our set, so that's 4, so 4 minus 1. Okay, take a minute and see what you get for that top calculation divided by 3. What are we going to divide by 3? Press pause, check it out. What I ended up getting was 20 divided by 3, or a value of 6.6 repeating. But remember, technically what we've calculated right now is variance. So to make this officially sample standard deviation, what we need to do is take the square roots of these answers. So when I do second square root on my calculator, I got an answer of, and I'll make this approximately, 2.58. So what does that describe? The average distance the values in my set are from the mean, or the average distance a number is in my data set from the value of 5, is approximately 2.58. And that's that. Now technically, I don't want you to have to do this by hand. I just wanted you to understand the calculation, and just a couple of things that you need to really catch here is that what we're doing is performing the operation of subtraction. So sometimes these values are going to be negative, like this one was negative 3, this one was negative 1. But what happens when you square these values? They become positive. So whether or not you have negative or positive values, the top part of this calculation can never ever result in a negative number. That's nice to know because we're taking the square root of it. We can't take the square root of a negative number, at least not get a real answer. The number of things that we have is always going to be greater than 1, so we're never going to divide by 0, because 1 by 1 would be 0. So, I don't know, why would you be calculating the standard deviation of one value? There is no variability if there's only one item. So a key piece to understand about standard deviation, it's always going to be 0 or greater than that. And if it's 0, that means that there's no variability in the set, which essentially is saying that all of the values in the set are the same number. The bigger this number gets, the more variability there is in the set itself with respect to the mean. So if the mean was 100 and my standard deviation was 10, I wouldn't think it's that big of a deal. If my mean was 5 and my standard deviation was 10, I'd say, wow, those numbers are all over the place. The standard deviation is larger than the mean. That's a crazy amount of variation. Well, if I don't want you to calculate it by hand, how do I want you to calculate it? By going into your calculator, first and foremost, when you see a list of data, going to Stat, Edit, and putting the data in your list. And then the first thing you'd want to do is to go run one variable statistics on that data and grab your mean, which is x bar on the calculator, and then your standard deviation of x, which says SX on the calculator, and for this one, of course, it says 5 and 2.58. And there's some more stuff to follow, but that's a good approximation to the nearest hundredth. Last class, we had a handout, so you might want to pause this, dig out that handout, and make sure that this data is somewhere in a list in your calculator. Now, I'm going to answer B first, because B is just a matter of me going to my calculator and calculating the sample mean, which is 236.25 according to my calculator, and standard deviation is 103.43 according to my calculator. Now, since this has to do with repair bills, right here it says this has to do with repair bills, so I'm just going to put the appropriate units. Remember, quantitative data has units, and standard deviation and mean both have the exact same units, the original units of the problem. American dollars, which is why I rounded off to the nearest hundredth on the standard deviation this time, because that's as far as we go in American currency. Now the histogram. What I'd recommend is hitting stat on your calculator, and the second choice there says sort A, and then the third is sort D. That just has to do with sorting your data in order. So I'm going to go ahead and sort my data in ascending order. And so when I hit sort A, it asks for a list. I tell it the list, and then I hit enter, and you should see the words done. Now hit stat and go take a look at your values. Now I could have also just gone with the one variable stats that I just created and looked for the same exact thing, which is what I'm looking for right now, is the min and the max value. The smallest value that I have, my min value, is equal to 56, and my max value is equal to 422. So the way I see it, if I want to make a histogram, I'm looking to make some bin widths, and so what should this space count for? So to make matters easy, what I do is I say I go a little under the 50, or 56 rather, I call that 50, and then I go to 450, and I subtract those values, 450 minus 50, and I get 400. If I use bin widths of approximately 50, if I divide this number by 5, because my rule is sort of like, I'd like around 5 bins for a small set of data, my bin widths should be widths of 80. Now, if I divided the number by 5 and it didn't go in nicely, I would just use the closest approximation for the bin width to the value I got. Say you divided by 5 and you got to 43.279. Well, then just call that 45. All right? Make this work for you. Don't work too hard for it. All right? Let's try this by hand now. First, sketch yourself a nice little clean-looking setup for a histogram and start making some notches. That first one is going to be worth 80, 160, so on and so forth. And just get a couple of notches going. We don't know how high we're going to go. We just want to make sure that they're evenly spaced. Now press pause and put some labels on these things. Here's what I've come up with. I have values of 80, 160, 240, 320, 400, 480. Down here in the bottom, my horizontal axis is the variable that we're talking about, repair cost, in dollars with the units, and over here is my frequency. Now what you want to do is go back to your calculator, stat, edit, go look at that list. It's in order, and what you want to do is you want to sort of run down that list. So just to go, an example, the first thing I have is 56, then 88, then 118, 143, 154, 172. And what I want to do is I want to compare these values to my cutoffs. Now remember, in this first bin is anything from $0 all the way to 80. And who fits that bill? One item. For the next one, it's going to be anywhere from $80 up to, but not including, 160. So that's all of these guys right here. And then so on and so forth. So the next one's going to land into the next bin. So for frequency, for 0 to 80, I'm going to have 1, and yada, yada, yada. So as I go through my bins, I'm going to count the frequency. So I'm just writing this on a piece of paper and keeping track of how many items in my list fall into each of the corresponding bins. according to my calculations, my first bin has 1 thing, my second one has 4, my third bin is going to have 6, 5 in this one, 2 in this one, and 2 in this one. Of course, there's nothing more than $480 in my list. So, since I have the highest frequency count of 6, what I'm going to do is just sort of make a tick mark up here and call this 6. Halfway between that, this must be 3. So 1, 2, 3, 4, 5, 6. That's good enough for our little setup here. And so now let's continue to fill this in. My first bin has 1 item. My next bin has 4 items. From 160 to 140, I have 6 items, so that's all the way to the top. 240 to 320, I have 5 items, so that's right there. 320 to 400, I have 2 items. And I also have 2 items in the last one. Now, from this, I have a pretty good idea, interpretation of what the data looks like. It's skewed to the right, right? There's a little bit of a trail off here. A little bit of trail off to the right. Right there. It's definitely unimodal, has 1 mode, somewhere between 160 to 240, or the most popular amounts of repairs at this place apparently cost somewhere in that zone. And I have a minimum value at $56, a maximum at $422. And that's that. If you go into second y equals, a stat plot in your calculator, and take a quick look at this on your calculator, it creates a similar looking histogram, but not the same as ours because it doesn't break the bins up the same as we did. Is it the end of the world? No. It's just another way of looking at things. And I think that the calculators is an equally good idea. Part C, is it appropriate to use the mean and standard deviation to summarize these data? Well, the big question is the data unimodal and, more importantly, symmetrical? Or if you look at your one variable stats, is the sample mean and are the sample mean and the median pretty close? If they are, then yeah, go for it. Use the mean. If they're too far off, use the median. This one seems to be a little bit skewed the way that I laid it out, so I would prefer to describe the association of repair costs using the values that I like to use when I'm describing skewed data. So for our description then, I'm going to say that the typical cost of repairs seems to be between $163 and $302, which, by the way, are my Q1 and Q3 respectively. I'm using Q1 and Q3 because I'm choosing to talk about the median, right? So between $163 and $302 with a median of $220. The min and max repair costs were $56 and $422 respectively. That's it. Just get in and get out. Don't make a big deal about this. Might be worthy to say that the data was just slightly skewed right, which means that although there were a couple of high-priced fixes, those were more of oddities than anything else, that the bulk of the repairs seem to be between these costs. What I want you guys to do now is to read this paragraph and answer these questions first. Take a second now. Press pause. So how'd you do? If a student comes in and gets 100 when the biggest score was at 90, it's the same thing it would do to anybody's average. The highest score goes up, then your average is going to, of course, go up. The median is the middle value after all of the data is in order. So although you added an extra score to the set, it essentially stays the same. That middle value is still pretty much in the middle. The range, largest, right? That's your max minus min. That's going to get larger, right? Because the distance between them got larger. The IQR, that's the distance between Q1 and Q3. So that distance is going to stay the same. Those are measures of position. And this last one is that standard deviation. What happens? The standard deviation is going to go up, but not because 100 is only because 100 is bigger than 92, but because the new value was more extreme than any value in the data set. So if the smallest value was a 28 and then the new kid came in and got a 16, the standard deviation still would have went up because the variability would have increased. See you next class.